Okay, well, it's nice to talk here again. So today I was just going to take a leisurely stroll through phase tropical hypersurfaces and try to discuss maybe one or two things I haven't mentioned about them, and about the proof that they form homeomorphic manifolds to hypersurfaces, complex hypersurfaces. So here's the outline. So first I'll talk about just the definition, basic properties, and then second, some elements, proof of Viro's theorem. Well, I guess it's conjecture, but now a theorem. And then applications to mirror symmetry. So, okay, so part one. I'm going to start with just assuming that I have some finite set, as many of my talks start with assuming that A is a finite set of some lattice. And dimensions. And I'll write M, the dual of N. And I'm going to choose a generic function on A, which is called eta. And it can be R valued, but I want to assume it to be integer valued for later. And generic, maybe I'll say something in a bit. And then we can consider a convex function which I'll take to be just lowercase trop eta, and it's going to send MR from tensor R to R, defined by just taking this minimum of pairing. So I guess if I put in M, this will be a M plus eta. Okay. So this function then induces a polyhedral polyhedral decomposition of MR. And the codimension one part. So let me call this something. Let me call this polyhedral decomposition capital trop. So here I'll include all of the strata, even the maximal strata. R. The codimension one part of this is the tropical variety, or tropical hypersurface. Used by eta. General background. So there are a lot of examples that people play with, but kind of the main examples to consider maybe one would be to take just some basis vectors. So here we have this polytope, and then our, I guess we have this is our tropical variety. Of course, you can go into 3 dimensions. And which is where, so I have some pictures. So this is the tropical variety for this guy here. So good. So these are the tropical varieties here. These are tropical pairs of pants, and they'll be sort of the point of focus with that. All right, so there's a dual decomposition, and it's helpful to have both decompositions in mind. You can play one off the other. So this decomposition of this polyhedral thing is happening. The polyhedral decomposition of MR is one thing you get from this, but there's a dual decomposition, which is a coherent subdivision. The convex hull of A. This is a polytope decomposition, and so we'll call this S. S. So beta. And there's a bijection between these. It's a dual decomposition, so there's a bijection between the strata of polytopes, so polyhedra. Theta to this inclusion reversing. And then, as I said, well, maybe I'll just show, if I have a polytope here, I'll write its corresponding polyhedra as sigma check. So now what is generic? So for generic choice, beta, this subdivision is a triangulation. And what I want to do is I want to use, I'm going to assume that, and then I want to construct several different different structures from this. So let's assume this. And what we'll do is we'll take a sigma, which is going to be a simplex, and I'm going to construct several things. So one thing is I'm going to construct a subgroup, M sub sigma, I'll call it M sub sigma, which contains M. It's contained in R, not necessarily a lattice. And then I will construct a polyhedra, an open polyhedra. Won't take too long. It's called P sigma, which is contained in MR. And then something that we'll call the co-amoeba cover. Sigma. And then finally, look at the co-amoeba, of course, associated to sigma. just going to simply be quotienting by m. All right, so in order to do this, I'll make an association. So I want to associate, so identify sigma with its vertices, and these are vertices in A. So I'll just think of sigma as a subset of A. It helps to think of it as an actual simplex, but okay, we can make that identification. And then, okay, so now let's define all of these structures. So M sigma, this is going to be the set of points, say M and M, so that when I pair with any element A, I have an integer. Pardon me. I need to not pair with any element A, but the difference of two elements in sigma. Okay. So this gives us a subgroup, and certainly, so certainly M is contained in this because my elements A were contained in the dual. Good. P sigma is going to be, looks a little awkward at first, but get used to it. Here, I'm going to take the absolute value of the pairing, and I'm going to let it be less than or equal to 1/2. And again, this is for all A prime. I guess I want the open polyhedra, so I'll make this strictly less than 1/2. And then what I want to do is, so this is some open polyhedra, and what I want to do is sort of not quite tessellate, not at all tessellate really, but I want to move this polyhedra around in M, and then I want to excise what I get. So I'm going to call this C tilde sigma. This is going to be all of MR, but I'm going to get rid of all of the translates P sigma by M. Pardon me. Yeah. Here I need M sigma. And finally, and then I've already defined C sigma, but I'll just write it down again. It's just this quotient. So this lives in this torus. So what these things look like, well, so the pictures here are, again, if we just look at this two-dimensional example, so two-dimensional example, and well, we have this picture here. This is, M sigma in this case is just all of M, and the P sigma will be some kind of open hexagon like this. And we'll see a picture of them. When you take this, you can tessellate, and as I said, I'll show a picture of that for the co-amoeba cover in a moment. But maybe, and it certainly looks maybe invented or something, but let me just explain where some of these things come from, in particular where this co-amoeba comes from. So here's a fact. So let's suppose I take the following function, Rho polynomial, which is just the sum of my vertices of sigma, C to the A, And so this is a Laurent polynomial in the group ring of n. And I have an argument map, which naturally lands, which naturally takes the torus to the, the complex torus to the real torus. And what we can do is we can see that the C sigma, I'm not sure if I need to translate here, but I think I'm okay, but may need to translate. It's going to be the, now this argument map, I'm maybe divide by 2 pi or something. So there's a question of a factor pi, but this is going to naturally be equal to the closure of the argument of the 0 locus. So this is a co-amoeba in the usual sense, but it's a co-amoeba of just sort of the restriction of the polynomial, the Laurent polynomial, to the monomials that are vertices of sigma. Okay, and so from this data, we can then define the phase tropical variety, or hypersurface, I should say. Okay. Phase tropical hypersurface is, I should say maybe induced by eta. Eta is this following space, just I'll write it as script T, eta. That's going to be the union over all of my simplices in the subdivision given by eta, or the triangulation given by eta. And then I'll take the dual part of the polyhedral decomposition and cross that with the co-amoeba corresponding to it. So this is going to be inside of the torus, and we can write it as side of MR, complex torus. All right. So this definition is due to many people. I mean, Mikhalkin has some, maybe called it the complex tropical variety or something, and Nice had some papers on this and others. So let me draw some examples. So one thing I like about this sort of hands-on definition is you can easily draw some pictures, but so one picture that wouldn't be from a simplex is we could take something like this, and I guess what I wanted to do is draw a subdivision of this guy, and then well, the tropical variety is it's not hard to draw. You get some picture like this, and I'm drawing this particular example because here we have there's some multiplicities on one of these edges coming out, and you can see this geometrically as follows. So this will be the phase tropical hypersurface, of course, admits a map just projecting to the first factor. So you can project to the tropical. Here I'm confusing notation, but I want to say this will project to the tropical hypersurface, not just the subdivision. and does so. So over these, all of the legs except this leg with the 2, it's just, we have a circle fiber. Pardon me, I have to move this over. So this guy's over here, and we have circles lying over these guys. But over here we'll have 2 circles. And the interesting, so along the legs you'll just have tori, so it looks like an integrable system, or an SYZ vibration, but then things get a little bit messy on these vertices, but it's not too bad. And so I'll look at this this picture, say around this vertex, which is corresponding to this triangle, and let's see what we have. We have this this picture here. This is the picture of the coamoeba cover. So what you'll have here is, oops, I only cut out a triangle. Sorry about that. Well, what you have here is you'll have these black dots. Let me say what it is. These black dots, they're giving you the fundamental domain, and or the lattice M, I should say. And then the red is essentially your coamoeba cover. So if you quotient out by the black dots, you'll get this the coamoeba. And in this case, you can see that there's two regions here where there's some holes, and well, that's in contrast, I guess, to the case when you have a unimodular setup. But this comes sort of for free, this lack of unimodularity. All right, so these are the pictures that we have for phase tropical, and that gives the definition of the phase tropical. Maybe I should have said, of course, if I just look at this part, you're going to get this kind of picture, which you can draw without going to the cover, where it's, you have sort of this kind of plumbing looking picture. And then here you'll get 2 triangles, one on either side, and those are the triangles coming in a picture like this here, once you fold them up. All right, so that's the end of part 1, the definition, basic structure. All right, so for part 2, I want to talk a little bit about Viro's conjecture, and then just a few ingredients in the proof. I mean, the proof is fairly long, but I want to give people an idea of what went into it. So again, one thing we can do with A is a set of lattice points, but we can take A as a set of exponents. And consider the Laurent polynomial with generic coefficients. So maybe I'll just say A. So I want C to be generic so that I can ensure smoothness and well, good behavior at infinity. And then we have Viro's conjecture, which says the following. Is that the 0 locus of F is homeomorphic to the phase tropical. Really for any eta. Eta is not so important in that statement. So what are the ingredients to proving this? Well, the first thing is we want to use Mikhalkin's pair of pants decomposition, which occurs on the complex side, the VF side, to reduce to the pair of pants case. So maybe I'll say it this way, to reduce to the case where A is a standard simplex. So A is equal to these examples I was talking about before, maybe. So you need to do two things. You need to get this decomposition into pairs of pants, but then you need to also realize that if you don't have a unimodular one, that you're just really your hypersurface is a cover of a pair of pants, and so you can work through that level. And then the more difficult thing is then to address the pair of pants case. And so for that, the strategy we use, this is of course this is all joined with Ilya Zharkov. The strategy we used was to describe regular CW complexes on both sides, on both VF and T. And here I can just drop the eta. It doesn't really matter. It's maybe I'll just call it n minus 1 since we're dealing with n minus 1 dimensional pair of pants. Now I should emphasize that this is a very easy theorem in the case when n is 2. So when you're dealing with one dimensional, this is not a hard thing to prove at all. So this is really the most difficult aspect of this is to deal with higher dimensional pairs of pants and to establish. And one of the things that comes into play there is showing that this is a regular CW complex on the phase tropical side. So there's natural strata that live there, but you want to make sure that this is that these ball closures are in fact balls. And so one of the obstructions to this is showing, so we want to also show that this guy is in fact a manifold, topological manifold. Everything is topological here too. There's no way to, well, I don't know of a way to naturally put any smooth structure on this. All right. So I want to just briefly say how this was taken care of, because I really like the answer here, or at least an answer, an approach to this. I think it's kind of interesting in and of itself. Okay, good. So, well, so where are the hard parts to where this is not a manifold? So if I went back and I looked at my original, say the two-dimensional case, so in the tropical variety here, over these strata, we do have tori as the fibers of the phase tropical. So this is pretty nice. Definitely a manifold, no problem there. Here it's less so, but there's sort of a one-dimensional level of there's a one-dimensional space of that you can act on to kind of reduce it down to lower dimensional case, so the one-dimensional case, or yeah, the one-dimensional case. So the real interesting and difficult issue happens over the vertice, over the vertex, over zero really. And so what you want to do is you want to take a look at what's happening over zero and ask what does the coamoeba look like there, and then what does the local structure look like of the whole phase tropical at some of the most difficult points of the coamoeba. And so to explain what that looks like, I'm going to just sort of, I don't know, come from a different perspective and just define something that is on its own, I think, understandable. So now I'm going to take an arbitrary Q, and here I'm just going to go to Rn, so I don't confuse myself, and I'll take B to be its vertices. So this is a polytope. So polytope, compact polyhedral. And then again, I can take this tropical thing, which is just yeah. So I can just take this tropical function, and I'll call it f sub q in this case, from Rn to R. And this is just the minimum. Since I'm just doing zero, this is just the minimum. Fq is just the minimum of all of the V viewed as a function on the dual. So maybe I can the dual. And I can consider its graph. And now I want to talk about, okay, so now for any element, say x in Rn, the Rn dual, I can define the gradient of x, the gradient of, not of x, but the gradient of fq at x. And this is going to equal a set of things. So this is a PL function, fq. It's not smooth. So I'm going to define what I mean by gradient. All these functions. I'll explain what they look like in a moment. All the functions that essentially support the graph. So let me give an example of all of this. So let's just say I take an interval, this, then my FQ will look something like this. Maybe I'm drawing the opposite, I don't know. And now if my X is over here, so if my X is here, I need to consider, the gradient will just consist of the linear function, which is just precisely this guy, because this is the only linear function that supports essentially this upper hull. Similarly, if I'm here, I'm on this side, the only function that supports it will be this. But if I'm at the origin, there's any function, any linear function that's, well, everything's taking 0 to 0. Any linear function that sort of sits between these two will be in the gradient of this function here at 0. So it's a set of linear functions. So now with this, you can define. We defined following subspace. So we called it the total supporting tangent space. We think of each of these elements in the gradient as being a supporting hyperplane. And what it does, what it is just, so this is, I'll say of this of FQ, or maybe the graph of FQ. And what it is following set. Call it graph. So it lives in the following space. We take the graph, and then at any point y, at any point x tilde, we take the evaluation of y x tilde, where y has to be in the gradient of FQ at x. And this lives inside of our 2n plus 2. So if you had if you just defined a smooth, if you just had a smooth function FQ, this would just be the tangent space inside of as a subspace of the tangent space of Rn plus 1. So, so the picture that I was drawing up here, we can draw the picture. So here we'll have spaces in the second factor that will just be the linear, the line associated to this ray, and then over this guy we'll have the line associated to this ray, and then over this one point we'll have this kind of a space. That's what lives over that middle point. And there's a lemma, which is that this is this key ingredient, or one of the key ingredients is that this is homeomorphic to R2n. In fact, this is a topological. It doesn't look very topological, or it doesn't look very much like a manifold, but it is indeed a topological manifold. So, and again, if you're looking at one dimension, like if we look at this picture here, it's not too hard to paste together these two-dimensional bits and see that this is indeed homeomorphic to R2. But then when you look at one of these manifolds, right? If this is my original polytope was a square or something of this sort, you'll get that this is the graph of FQ here. And then over varying strata, so over this red strata, you'll get these two planes and everything sort of lying between these two planes. But then at the origin, you sort of take the positive and the negative and just get rid of them, and it's everything in between. And you start to see that it becomes a little less clear that this is a topological manifold. But nonetheless, what you can do is you can look at this structure and project to the x tilde factor. So if you project, so the basic idea here of how to prove this is project to the x tilde factor and use convexity. This function fq is convex, and so you want to use convexity. In fact, you can project to this x tilde factor, and then what you'll get is you'll get a space that is essentially looks like a staircase. So I was just going to show a picture of what you get there. So if we did this with this particular Q, if I project and let's say my x tilde is here, then what you're getting is on these regions, the gradient is unique. It's just that linear function, so you'll get a constant value when you evaluate those gradients on x tilde. And then when you pass one of these regions, you're going to kind of move up. You have lots of different gradients, but they sort of move you in one direction. And again, so for each of these maximal guys, you'll have these sort of stairs that you can step on. And then as you move from one stair to the other, you have this bending. But what you can show using convexity is that this is indeed homeomorphic to R2. And then because you're just projecting, you get something homeomorphic to R2 cross R2. And in fact, as you sort of move x tilde around, you can sort of see maybe an escalator type picture. These stairs sort of start to come together and move apart. So it's kind of a nice geometric picture of what you get. Okay. So that's the idea. I mean, it'd be nice to. I see a chat. Maybe it's a question. The steps capture the mean curvature. What about the Gauss curvature? I'd like to be able to answer that question. I don't think I can though right now. All right, so let me so continuing. We want to just make an observation, and this is sort of why these lemmas are important, which is that so at a vertex, sorry, the local fan at a vertex of this polytope, which is this zone. So recall in the Comi, what we did is we have these polyhedra, and if we're in a pair of pants, we have and we take all of A, the polyhedra we have is going to be a polytope, and this is this zonotope that people have looked at in various investigations of mirror symmetry. And basically, you take this zonotope and you don't quite tessellate, you move it around, but the sort of the critical points there, the points where you have the worst amount of, well, the most curious type of behavior would be where these vertices of this polytope meets a translate of itself. And so if you take the local fan of the phase tropical, so of this phase tropical at one of these guys, then this is the observation is that this is equivalent to one of these guys, to a totaled tangent space. And in fact, here, we can even say what Q is. Q is going to be a product of two simplices. So I'll just say maybe K. So this gives us some control over what what the local structure looks like near these vertices of the phase tropical variety. All right. Okay, so that was it for part 2, and then I was going to make some motivational statements about why we would want to consider this thing in the first place. So maybe some advantages of considering this. So the first advantage, so this polyhedral structure is very explicit. So in this guy, explicit. And we see some things that, well, that may be hard to identify otherwise. So, so in particular, one thing that we're interested in, one of the reasons we're originally interested in this was to try to study mirror symmetry, and so so if we start with a pair of pants, for example, so starting with a pair of pants, in the more general cases, a little bit more cheap. We can look at this maximal. Well, first of all, as I said, there's this description. So there's a description, simple description, of this polytope I have, and let me take the closure of it as just as a zonotope, which is just a Minkowski sum of, maybe these are the duals, but okay. 0 to n, and here E0 is maybe the sum of all the other i's by definition. So you have this nice explicit description, and there is a description of the faces of this zonotope, and in particular, you can describe the following space. Let me say, if I'm given, sigma in AI, or sigma in A, pardon me, we can take Q sub sigma to equal this sum over all sigma. So each of these i's over in this description, we can think of them as supporting faces of the simplex, and so I can take all of the I for which sigma is not contained in Fi, and I can take the Minkowski sum of just these guys, and then I can do the following thing. I can take, so this is a polytope in M, it's defined correctly, MR. I can define the following thing. I can take sigma dual, which is also an M. I can cross it with Q sigma, and I can intersect it. So here, maybe what I want to do is take this inside of the quotient by M, but I can intersect this with a phase tropical. And so this is then going to give me, this construction gives you essentially the boundary of a half open ball, and it's homeomorphic to Rn-1 sitting inside of this pair of pants. And so, and as I said, we can do this for any sigma. If you take, so taking sigma to equal everything, so in other words, equal A, so this just gives sort of the boundary of this, this polytope, which was first, I think this as a maybe as a sphere, it can be thought of as this sphere in Sheridan's proof of homological mirror symmetry. So yeah, I had some picture. Let's see if I can. I had a picture. Yeah, this is the zonotope in 3 dimensions. And so, as I was saying, this is so you can kind of see this as a cube. Say maybe this is the bottom part of the cube, and then the Minkowski sum is with these edges. So you can see, I think you can see the Minkowski sum here. And so this example I was just talking about would be the boundary of this cube inside of a torus. So once you quotient it by m, you would get some sphere that's maybe immersed. I mean, is immersed, in fact, well, in a polyhedral sense. Okay. But then there are other strata too, and so we can look at these. And so this would be a picture, again, of this 2-dimensional picture. You can take this cone here, and then that polytope I just described, this P sub, what do they call it, Q sub sigma? Well, this Minkowski sum, this is going to be the square, and over the origin, you'll get this filled in square, and over these lines, you just get this edge. Over this line, you'll get this edge, pair of edges, and then in the interior, you just get 2 copies of this cone on top of each other. And so you can see this is the boundary of some 3-dimensional ball. So this will give you some sort of thimble. This is the idea. So we're trying to construct Lagrangian, topological versions of these Lagrangian thimbles. So this was maybe one of the advertisements for why we're interested, is that we can get some topological control over good candidates of Lagrangians, and we can try to work out some of the Fukaya calculations or symplectic geometry with these tools. So in fact, we've made a little progress. That what I'm venturing into now is a work in progress with Ilya. And so under various circumstances, we can do this, what I just described, we can do it for the pair of pants. But as I said, there's this way of gluing together pairs of pants to make the whole hypersurface, the whole phase tropical hypersurface. And so under various conditions, these symbols glue to give immersed spheres in hypersurface in T eta. So where now you have something more general. And the mirror statement that we're looking at now is, and I think we should finish up hopefully pretty soon, is the conjecture for graded matrix factorizations. Here, this is an n+1 dimensional toric variety, and with a particular potential, and we want to associate this to some wrapped Fukaya category on the hypersurface, which is this V. So what we have, using phase tropical techniques is difficult to make a lot of statements about wrapped Fukayas because we've lost some of the smoothness, and we've certainly lost symplectic structure, but we have intersections, and we can talk about candidates as combinatorial candidates for what discounting looks like. And so we're not directly addressing this, but we're giving a sort of intermediate category to explain this equivalence in a polyhedral setting. And then the third application, I would say, for this is that, well, so I have a, okay, so one, maybe I can quickly do one other application. So one other thing to say is that this map, eta, from a tropical standpoint, tropically, stands for a deformation, so our family of hypersurfaces. In particular, right, what you do in tropical geometry is you really work over a valued field, and you want to consider, you don't want to consider really f. What you want to consider is you want to consider this t to the a to a, x to the a, maybe with the coefficients if you want. And so this gives you a family of hypersurfaces. And there's also, so now we have maybe -0, we have a family of hypersurfaces. And one might be interested in, of course, this monodromy around the origin. And there is, so then the point I wanted to make here was that there is a natural monodromy map on this on the space tropical level, which is kind of fun to write down. Which just takes x comma x tilde. Remember, x is in the tropical variety and x tilde is in the coamoeba over whatever particular strata, and it just maps to x and x tilde plus x. So this gives a natural candidate for the monodromy map. This we haven't proved quite yet, but I think this is forthcoming. And then the final application I wanted to mention was that of like skeletology. I don't know if that's a word. Skeleton. Let's say that. And so if you drift into this polyhedral decomposition, there are a lot of different versions of skeleton for hypersurface as well as the complex torus itself, where you can start to see you can see these things in the phase tropical world. So one example, I think I only have time for one example, is well, maybe Nadler and Gamage. They talk about this permutahedral, and probably others talk about this quotient of the permutahedron. And what you can see with this tessellation that I was, that's not quite tessellation, with this polytope, as you move it around in corresponding to pair of pants, as you can see the following picture that I'll share, which is right here. So this is what, so as I said, you take this polyhedra and then you move it around by m in the unimodular case, or m sub sigma. And what that does is that it doesn't quite tessellate, there's a lot of room, but what you can prove is that this, in the case of the pair of pants, the unimodular pair of pants, what happens is you have, this is in some sense dual to the permutahedral tiling that exists already. So when we take the quotient of that permutahedral tiling, we'll see some Lagrangian skeleton, which is indeed the quotient of the permutahedra. So yeah, so these structures exist naturally in this setting. I think I'll stop there and I'm right at time, I think.
Questions?
Oh, actually, I have a question, Gabe.
Okay.
Hi. So you mentioned about the monodromy around the t equal to 0 fiber.
Yeah.
Do you also consider other kinds of singular fibers? For example, if you take this t not as a formal or small parameter, let t be large. Is it possible you have other singular fibers and going around those?
Yeah, well, one thing I did consider is, I mean, one thing you can certainly do is you can take the pair of pans. So as you well know, and you can consider different Landau-Ginzburg models on it that arise in the mirror symmetry of your talk from a couple of weeks ago. Once you unfold them. And so, and in those cases, I was going to say something about those, but those cases, I don't see the monodromy like I see it here. But you can describe, you can give a picture of the geometry for those, at least in low dimensions, I can give a picture for what the geometry looks like there. So I haven't, there are two types of, there's two types of kind of general monodromy that happen, right, with these spaces. One is to sort of twist around the sphere. I mean, two basic types, and one is to sort of go near this limit at infinity. And so this type of monodromy, I think, is more that limit at infinity. Okay. The other one is but what we can do is we can isolate. Well, we believe we can isolate the topological sphere through this process, and so there we can, well, at least in principle, we can say what the monodromy would be around a critical point.
Okay, that would be really cool. Okay,
yes.
More questions? All right, then. Thank you, Gabe. And next week we'll have Diaconescu, but not in the conventional time. Yeah, it will be in the morning. Okay.
Thank you.
Thank you.